Hello everyone, welcome to this video of connecting the dots in physics. In this video, we want to discuss the difference between the mechanical momentum and canonical momentum. Mechanical momentum here refers to this product m into q dot. Qi here is the generalized coordinate and qi dot is the corresponding generalized velocity. Since q may not have dimensions of length, it may happen that p also don't have the dimensions of momentum, where the dimensions of momentum are kg meter per second. So it may happen depending on what is the generalized coordinate. Generalized velocity will have a different dimensions than velocity, and in that case mechanical momentum will have different dimensions than the momentum itself, which is kg meter per second. Canonical momentum refers to quantity which is obtained by differentiating L, which is Lagrangian, with respect to q dot partially. Again, if the system has n number of degrees of freedom, I have to write it with subscript where I runs from 1 to n. Once you have this momentum, then Hamiltonian is obtained by this equation pi qi dot minus L. Note here that h is always written as a function of q, p and t. Q is the generalized coordinate, p is the canonical momentum, and in general it may be function of time. Similarly, L is function of q, q dot and t. While writing this equation, we are using the summation conventions. Since we have two subscript in this first term, that means the subscript runs from all the possible values of I, which is from 1 to n. So basically that term is this summation of I running from 1 to n pi qi dot. Now to compare the difference between this canonical momentum and mechanical momentum, we will consider three particular cases. Let's start with the first one. This is the problem which we considered in one of the previous lectures. It is a ring rolling down the inclined plane, where this incline makes an angle theta with the horizontal, and this ring is rolling on that incline and not sliding. So because of the friction, the ring rolls, and therefore its kinetic energy now has two components. One is the kinetic energy due to the linear motion, and the second component is kinetic energy of rotation of that ring. So we have to keep that in mind. When we solve that problem, we simply use the concept of mechanical momentum here. P is equal to mx dot, and when we use that, plug that into this Hamiltonian and obtain acceleration, which is this, then that turns out to be equal to g sine theta. Actually, the acceleration should have been g sine theta divided by 2. Some of you may have already found out the mistake that we made in solving this problem using Hamiltonian. We solved it by using the other two formalisms, Newtonian and Lagrangian, which gave us the correct answer. But this one here went wrong, and now we will solve this problem in the correct way. So this is the problem again, which we have to solve using Hamiltonian now. Where do we start? We start with the Lagrangian. Lagrangian of the system is m x dot square plus mg x sine theta. This here is the kinetic energy, and this is minus of potential energy. I won't go into the details and calculate these kinetic energy and potential energy. If you have any confusion, you can go back to the previous video and see how we obtain it. So once we have the Lagrangian, next step is to obtain the canonical momentum. Now since there is only 1 degree of freedom now, which is x, which is basically this direction, and it is positive when it is moving downwards and is negative when it is moving upward. Canonical momentum is dou L by dou x dot that we can obtain, and it turns out to be equal to 2 into 2 into m x dot. So this is the canonical momentum. Now you can already see that canonical momentum is 2mx dot. If we consider mechanical momentum for the system, it is simply m into x dot. So this factor of 2 which we have for canonical momentum is not there for mechanical momentum. So you can already see the difference between the two. Next step to obtain Hamiltonian is use the equation P into Q dot, which is x dot in this case, minus L. Now I don't have to worry about the summation here. There is only 1 degree of freedom, and this is equal to, I'll keep x dot as it is for now and use this P in the equation. So I get 2m x dot the whole square minus L is m x dot square minus m g x sine theta. Now this is equal to m x dot square minus mg x sine theta. Now what is next step? H that we have obtained here seems to be a function of x and x dot, but we want h to be a function of x p, and there is no explicit time dependence. So this can be done by using this equation again, concept of canonical momentum, where x dot is equal to p divided by 2m. I'll plug this back into this equation, and that gives me the Hamiltonian as a function of, sorry, this is h, Hamiltonian as a function of x and p, then is p square by 4m square minus mgx sine theta. This m and m gets cancelled and we are left with p square by 4m minus mgx sine theta. So this is our Hamiltonian. H is equal to p square by 4m minus mgx sine theta. Now next step is to use the Hamiltonian equation of motion. Hamiltonian equations of motion are p dot is equal to minus of dou h by dou q, and the second equation is q dot is equal to plus now dou h by dou p. We made a comment in previous lecture that Hamiltonian treats momentum generalized coordinate on the same footing. Therefore we get a kind of symmetric equations for motion, but they are not exactly symmetric because of this negative sign. So let's use this equation of motion for the Hamiltonian and try to obtain p dot is equal to minus, and this is when I differentiate h with respect to x, I'll get plus mg sine theta. Now to find out the acceleration, I have to use the canonical momentum because that is what it is. So what I get when I plug that here is 2m x double dot is equal to mg sine theta, and x dot or x double dot is g sine theta by 2. So now with this formalism we have obtained the correct answer in this fashion. What went wrong when we solved it in the previous video is we considered mechanical momentum instead of canonical momentum, and that's why we obtained the wrong answer. Otherwise the Hamiltonian, which is kinetic energy plus 2 potential energy, is correct, but we use the mechanical momentum. And now it should be clear that we have to use the canonical momentum, which may not be same as the mechanical momentum when we solve problems using Hamiltonian. Some of you have already noticed this pp1 here. There are of course some points to ponder in this video. Let's consider a couple of them. First one is the canonical momentum itself. P is equal to 2mx dot, which appears to be double of that of mechanical momentum. So it is 2 into p. So you can think what really does that mean, what that canonical momentum suggests. Now the second point to ponder, second pp, is on the next slide. The way I have solved this problem is not entirely correct. There is a catch, and as the slide suggests, catch me if you can. I chose this problem because it is a simple problem which in a way demonstrate how canonical momentum can be different than mechanical momentum. But as I said, the solution is not technically sound, it is not 100% correct. Though the acceleration that we obtain, which is simply the x double dot, which is g sine theta by 2, is correct, it is not wrong, the acceleration is not wrong. Let's see if you can find the catch here. Now next move on to the next slide. I said that we would consider 3 problems in this video. This slide is not for the second problem. I want to discuss something else before we move on to the other problems. This is simple Lagrangian equation, and if you have seen the derivation of it using D'Alembert's principle, you must have realized that the way this equation is obtained is like this. First you get a step which is something like this: qi dot minus dou L by dou qi, sorry, this is L. This T is nothing but the kinetic energy, and this turns out to be equal to Q, which is generalized force Qi, which is minus of dou U by dou Qi dot. So this is the generalized force that we get, and when we plug it here we get the Lagrangian equation of motion. Now it may happen that this U, which is potential energy, is not simply a function of Q and T. It could happen that this U is function of Q, Q dot and T, and when it happens this is called as velocity dependent potentials. When this happens, you can slightly modify the Lagrangian equation of motion and write it in this way. So what you do is you try to write this generalized force in such a way that it matches with the Lagrangian equation of motion. Note here that U is simply the potential energy, which is function of q dot. If you can write it in this fashion, then you can use the Lagrangian as kinetic energy. I'll write it as T minus U, and then use this Lagrangian in the Lagrangian equations of motion, and can solve the problem. One of the example is the drag force. When you have force which depends on the velocity, something like this, now we can have slight modification for this Lagrangian equation of motion. The difficulty here is when I consider this force, which is minus kx, its dimensions are that of force, whereas when we use U, it should have dimensions of energy. Note that q, which are generalized coordinate, may not have the dimensions of length, but L always has the dimensions of energy. So we have to arrange this, write this force in such a way that it can be used in Lagrangian, and for that we have to get a function which can give us this force. That can be done with Rayleigh's dissipation functions. Now equation of motion for this case is slightly different than this equation of motion. When we use this Rayleigh's dissipation function, I am leaving it as point to ponder for you. You can search the books and see what this Rayleigh's dissipation function is and how equation of motion is modified for Lagrangian. It doesn't now has this form. This form is called as Euler-Lagrange's equation. This equation of motion that you obtain for Rayleigh dissipation function is slightly different. It has one more term. I will leave it here for you to work on this velocity dependent potentials, Rayleigh's dissipation function and equation of motion. Let's move on to the next problem. This problem is of a charged particle which is placed in electromagnetic field. Now Lagrangian for this system is given here, that I have derived in the previous video. If you have skipped that video, it's alright. You can still try and work on this problem. Start with this L and try to obtain the equation for motion for the charged particle. Note that equation of motion for the charged particle is F is equal to Q into E plus V cross B, where V is the velocity of the particle and B is the magnetic field. This is one more point to ponder. What you have to do is use Lagrangian equation of motion, which is dou L by dou Q dot differentiated once with respect to time minus dou L by dou Q is equal to 0. So you have to use this Lagrangian, use this equation of motion, and with that you should obtain this ma dot is equal to Q into E plus V cross B. Of course, here since you don't see any B magnetic field, it is manifested through this vector potential A, which is such that del cross B is equal to A. You can try it, use all these three equations and try to obtain this equation of motion for the charged particle in electromagnetic field. I'm leaving that there. One more thing that you should note here is whenever these capitals are drawn in bold, that means these are the vectors. I'm using the standard conventions which are used by most of the textbooks. So this bold simply means that this A is a vector, which is the vector potential, and V also is a vector. Now let's obtain the conjugate momentum for this charged particle, for this Lagrangian. This Lagrangian is written for 3 dimensions. Since the particle can move in 3 dimensions, what I'll do is I'll consider only one component of these 3 dimensions, and therefore L can be written as half m x dot square minus q into phi plus q into a into x dot. Note here that I am not using ax, the subscript for a. This a here simply means that it is x component of the vector potential, and similarly this x dot I may use sign v, which means that it is velocity along x-axis. So conjugate momentum along x-axis, remember that we are doing only for one axis, is equal to dou L by dou x dot, which is equal to m x dot plus q into a. So p that we obtain is m x dot plus q into a. Now the same way we can obtain canonical momentum along y and z axis. What will change is this x dot will become y dot, and this a in this case is a along x-axis. It will now be along y-axis for y component, and for z component it will be a z. So you can it is straightforward to apply this for the three-dimensional case. So do you see the difference between the canonical momentum or conjugate momentum and the mechanical momentum? It is obviously there. Mechanical momentum, it's simply m into x dot even for along x-axis, but for x-axis conjugate momentum or canonical momentum is given by this relation. So definitely they are different. This is how you can write the conjugate momenta for all three coordinates. This I will run for 1 2 3 for the 3 dimensions that the particle is moving in. Now definitely it is not the mechanical momentum. Mechanical momentum is going to be simply m into xi dot. Now it's a point to ponder of what this pi really means, what is the physical significance of that. I'll leave you to think about. Now let's find out the Hamiltonian. H is pi qi dot minus L. P already I have calculated, it is m xi dot plus q into ai. What I'll do to get this H is I will first keep this H in terms of Qi dot or Xi dot in this case. So this is equal to Pi is M Xi dot minus plus Q into Ai into Xi dot minus Lagrangian is half M Xi dot whole square plus Q into phi minus Q into A I Xi dot. This is equal to M Xi dot whole square plus Q into AI Xi dot minus 1 by 2 M Xi dot square plus Q into phi minus A into AI. This is Q into AI Xi dot. Now this Q AI Xi dot gets cancelled, and here I have mxi dot whole square, and this is half of it. So this is equal to H is equal to 1 by 2 mxi dot square plus q phi. Let's continue this mathematical jugglery on the next slide. So H is equal to, what was it, 1 by 2 mxi dot square minus or plus q into phi. Am I correct? Yes. So now H has to be written in terms of P. Remember, it has to be written in terms of X, P. For that, I can use the relation for canonical momentum Xi. From this canonical momentum, if I rearrange the equation, I can write Xi as Pi minus Q into AI divided by M, and that Xi now I'll use in this equation. So I get 1 by 2 M into Pi minus Q AI divided by M whole square. I'll erase this, plus Q into phi. So H that we obtain, Hamiltonian that we obtain, is 1 by 2m into Pi minus Qai whole square plus Q into phi. In vector form, I can write this Hamiltonian that we have obtained in this fashion. I want to look back to the video in which we discussed the importance of Hamiltonian. In this case, H for charge particle is obtained like this. Now you can straightforward apply this equation of Hamiltonian in quantum mechanics. What changes in that case? So suppose this is the classical Hamiltonian that I have obtained. Now for quantum mechanics, what changes here? This Hamiltonian becomes an operator, and when it becomes an operator, this P is also an operator. If we are discussing semi-classical theory, where we are treating electromagnetic field as classical field of classical field through Maxwell's equation, this A then is a simple field, it is simple vector. But if you are considering field theory where you quantize field also, then this A also becomes the operator which corresponds to that magnetic potential for the field which represents the magnetic field, and this is Q into phi. So we have a great message here. Suppose I have Hamiltonian for a classical system, I have classical Hamiltonian for the system, and I want to consider quantum treatment for that system. All that changes is all these vectors, which are vectors for classical Hamiltonian, now becomes the operator in quantum mechanics case, and this is possible due to this h which treats p and x as separate coordinates. We will get back to this point when we consider the canonical transformations. For now, I'll leave this point here. So this is the Hamiltonian that we have obtained, and now we want to ponder upon a few things, upon a few points. First is this conjugate or canonical momentum. In this, P is clearly not the mechanical momentum, which would have been m into xi dot simply. This q into ai dot term is extra in this canonical or conjugate momentum. So what does that represent is one of the question. Similarly, if I write this Hamiltonian as a function of xi dot, which we have done in the beginning, it's here. So what we get is this equation. Now if you look at this equation, this is simply the kinetic energy of the particle, and q into phi is potential energy of the particle because it is present in this electric potential. This phi is nothing but the electric potential. Remember, when we derived this Lagrangian, we saw that this phi is electric potential. So you can think about it. Where does this A go for this particular case? If I write the Hamiltonian in this fashion as in terms of V, there is no A present there. There is no term which visibly corresponds to this A. Think about it. That's why it is a point to ponder. Now let's move on to the third example that I wanted to discuss in this video. It is not directly related with the Hamiltonian and Lagrangian formulation per se, but I have chosen this because in this example we will get the equation of motion, we will get the momentum which is not the mechanical momentum. And the example is this electron C. Suppose I have a metal. So for good conductors, what we have are the free electrons. These electrons are free to move inside the metal, and they are not bound to a particular site, they are not bound to a particular atom, and therefore in a way you can say that this metal is filled with sea of electrons, where these free electrons are free to move under externally applied force. If there is no external force applied, what happens is these electrons, due to virtue of temperature, as far as the conductor is not at 0 Kelvin, which is not possible. So as far as the metal is at non-zero temperature, because of the temperature, these electrons are continuously in motion, and the whole situation is random. So you have a piece of conductor and there are atoms, these sides. This is just a representative diagram that I am drawing here. It is just a schematic, and then what you have is these small electrons which are moving in all the random directions with random velocity. These velocities are of course have a particular distribution that you can check what kind of distribution these velocities of electron have, and as they move they undergo collisions, they collide among themselves. Electron collision, there is collision between the atoms and electrons, and the whole scenario is random. So everything, the whole situation is random, but yet from this randomness we can get a very nice ordered equation. Let's try to get it. Due to this complete randomness, a nice order emerges from the whole situation. This probability of any electron chosen at random going under collision per unit time now is same. It is given by this relation 1 by tau, where tau is called as relaxation time, or sometimes it is referred to as the mean free time. What does this exactly mean? It means, suppose that you observe all the electrons in the metal. Suppose you could observe all the electrons in that conductor. You choose a particular time, say t, and then note down how many electrons undergo the collision. So suppose n is the number of electrons which are undergoing collision and n is total number of electrons. Then this n by n will give you the probability that electrons undergo collision in time t, and this probability per unit time is simply n by n divided by this t. If you could perform this experiment, if you could try different times and find this quantity, and in large number of experiments, what you will observe is this quantity is always constant. It is given by this relation 1 by tau. Now you can see that why it is called as relaxation time, why this constant has the dimensions of time, because it is probability per unit time, so it should have dimensions of time inverse. So this complete randomness brings this order, and now due to this nice ordered probabilistic equation, we can find equation of motion for the electrons. So let's start here. Suppose these electrons are exposed to some external force f of t. This external force could be external electric field, or it could be external magnetic field, or something else. Now let's consider this quantity dt by tau. What do you think it gives us? 1 by t, remember, is probability that an electron undergoes collision, and we are multiplying it by this small time dt. Therefore it gives us probability that an electron will undergo collision. Now since there is external force F acting on each of these electrons, and we want to observe the effect of this force on the electrons as a whole, we are not worried about these electrons which undergo collision, because once they undergo collision, all the effect that they have picked up due to this force is gone. What we are interested in, number of electrons which do not undergo the collision, and probability of that happening is dt by tau, because there are only two possibilities that could happen. One possibility is that electron does undergo collision, and the second possibility is that the electrons do not undergo collision. And if dt by t is probability of one possibility, the other has the possibility of 1 minus the first possibility. So 1 minus dt by t is the probability that electrons doesn't undergo collision. This doesn't has to be underscored here, is probability that the electron doesn't undergo collision, then n into 1 minus dt by tau is the total number of electrons which do not undergo collision, where n is the total number of electrons present in the metal. And now we are interested in these electrons, because these carry the effect of this external force. So where do I start? I have to find out momentum of the electrons after time dt as they move under the influence of this external force F. This is equal to P of t, which is the initial momentum, plus dp, which is change that occurs in the momentum as their motion evolves with time. So this dp I can find out by using Newton's second law. This is what I know. This F is the external force, and we are trying to observe the effect of that external force on these electrons, and therefore dp is equal to F of t into dt. But does all the electron pick up this momentum? The answer is no, because n into 1 minus dt by tau, number of electrons have not undergone the collisions. The electrons which have undergone the collisions, they won't pick up this momentum, and we are interested in these electrons. So what is the total momentum which is picked up collectively by all these electrons as they move under the influence of this force? It is n into pt plus dp into 1 minus dt by tau. So let's work on this a bit to obtain. Now what I'll do is I'll divide it by n. So when I divide it by n, what I get is the average effect. So henceforward I won't mention this n, but when I write this equation now, it basically is the average change in the momentum of all the electrons. So here now we are talking about averages. So P of t plus dt is P of t minus P of t into dt by tau. This is not, it is dt by tau plus dp minus dp into dt by tau. So this is what we have. Remember that this is the average momentum that we get. Let's continue the calculations on the next page. This P of t plus dt is average momentum that electrons gain in interval dt. This is P of t minus P of t into dt by tau plus dp is f of t into dt minus f of t dt square. So this is what we get. So this is what we get when we bring this equation on the next with this right hand side for dp. So you can convince yourself that this is what we get. Now we will find out the average change in the momentum. P of t dt minus P of t is equal to, now let's first concentrate on this term. If I say that dt is tending to 0, it is infinitesimally small quantity, then I can equate this, or I can approximately say that this is equal to 0. And when this is equal to 0, approximately, with this error of course, we can write P of t plus dt minus P of t as f of t dt minus P of t into dt by tau. Now let's divide the whole equation by dt. So what I have is P of t plus dt minus P of t divided by dt is equal to f of t minus P of t by tau. This now is nothing but dp by dt, rate of change of momentum at time t, is given by f of t minus P of t by tau. Now if you think about this, it is a wonderful equation. I have written this equation here. What we have is a complete randomness where all these electrons are moving in all the possible directions, they are colliding with each other. But when we find out the average dp by dt, average rate with which the momentum changes, it follows a nice equation which is given by this. This F is the force due to the external field, which we can find out once given the field. And this term, this first term, velocity dependent potential. So this whole randomness boils down to nice order in form of this equation. Again, here we are talking about this momentum, which is not the mechanical momentum. It is average momentum of all the electrons which are there in that C. And mechanical momentum at any given point for the electron is going to be simply m into v, where this v is random, and this there is no point in discussing mechanical moment because of the huge number of electrons and the complete randomness. But from this randomness we get a nice equation of motion, and it is a wonderful thing. I find it very amusing that such an order should emerge from a complete randomness. That's all I wanted to say about mechanical versus canonical momentum in this video. But there is something else, and I will leave this video with this point to ponder: the exponential decay. You must have seen at so many places this equation of exponential decay. Suppose I have number of radioactive particles, then they decay like this: e to the power minus t by, where this tau is a constant which has the dimensions of time. Now since we discussed C of electrons, we can relate that to this exponential decay. What we have already said is that probability per unit time of the collision is 1 by tau, which emerges because of the randomness of the system. If I choose any electron at random from the metal, and if I find out for how long it goes in the metal, how long it moves in the metal before it undergoes collision, that on an average that time goes as e raised to minus t by tau. So as t increases, this gives me the probability, average probability, that the electron will not undergo collision. Let me again say what this e to the power minus t by tau is. If you choose one electron at random from the C, then this e to the power minus t by tau gives the average probability that the electron does not undergo collision for time t. I am leaving it as point to ponder at the end of the video. You can try to derive this exponential decay relation from starting from this equation of probability of collision per unit time for the electrons. These are the references that I have used for making this video. If you are registered for the course of connecting the dots in physics, and if you have any doubts, any corrections, or any modifications that you want to suggest in this video, you can put that in the forum, in the online forum. If you are watching this video on the YouTube, please put your suggestions or corrections in the comment section. Thank you for watching this video.